Okay, so this will be the last of the first part of the preview that I need you guys um, to look at for the beginning part of chapter 16. Okay, so in a binomial setting, we can define a random variable as the number of successes in a set number of independent trials. So what's the probability distribution of X then? So we're going to take this video to look at kind of two examples to help kind of shed some light on the probability distribution of these binomial random variables. Okay. So here's kind of the first situation that we're going to set up, okay? And we'll look at this again and be more precise with it. So so now we're going back to that problem that we identified as being binary. So each child of a particular set of parents has probability of 0.25 of having type O blood. Genetics says that children receive genes from each of their parents independently. If these parents have 5 children, the count random variable X of children with type O blood is a binomial random variable with n equaling 5 trials, and the probability P would be 0.25 of success on each trial. So in this setting, a child with type O blood is a success, and a child with another type of blood would be a failure. Okay, so we already kind of identified this in the last video as definitely being a binary setting. So we know that already. Okay, so let's talk about the idea of our probability that our random variable will equal 0. So in other words, what's the probability that none of the children will have type O blood? None of the 5 children would have type O blood. It's the chance that all 5 children don't have type O blood. The probability that any one of the couple's children doesn't have type O blood is 1 minus 0.25. So that's the complement rule, right? So the multiplication rule for independent events that we learned back in chapter 14 would tell us that I'm going to multiply the probability of a failure or not type O blood 5 times. So the probability that the first child will have a blood type other than O would be 0.75 times the second child, times the third child, times the fourth, the fifth, would give us a probability that all 5 children would not have type O blood would be 0.2373. Makes total sense to us. That's not anything new, okay? How about if I asked you if one child were to have type O blood? So there are several different ways in which exactly one of the 5 children could have type O blood. So for example, the firstborn might have type O blood, but the remaining 4 children wouldn't have type O blood, right? So we would kind of set this up as the probability of the first child being a success, but the next 4 being a fail, okay? So I know that they're independent, which means if I'm looking for the total probability here, I could just multiply, right? The probability that the first child will be a success would be the probability that the first child have type O blood, which they told us would be 0.25, right? Times the probability that the second would have anything other than type O blood, so that would be the complement, 0.75, and the next 4 are going to have the same probability. That's a fail, okay? So 0.25 times 0.75 to the 4th, right? Or the possibility here could also be that the first child didn't have, but the second child did have the type O blood, right? So that would be that, again, one child would be you would have one child be a success, okay? But the next 4 would be a fail, or the other 4, I should say, would be a fail, okay? Or the first 2 would be a fail, and the third child would be a success. You still have 1 success times 4 fails. or the first three would not have type O, and the fourth one would have type O. Again, 1 probability of a success times 4 probability that it's a fail. And then finally, the last child, the last of the 5 children could have type O, where the first 4 didn't, and it would still be the 1 success times 4 fails, okay? In all of these, there are 5 different ways in which exactly 1 child would have type O blood, each with the same probability of occurring, okay? So, uh, so as far as our probability is concerned, the probability that first child or 1 child would have type O blood would be all of these put together, okay? So I have this plus this plus this one plus this one plus this one, okay? So 5 times the 0.25 times the 0.75 to the fourth, because you're going to have 4 fails and 1 success. And you're going to have that in 5 different ways that this can occur. Is it the first success? Is it the second one success? The third child a success? The fourth or the fifth child a success? So there's about exactly a 40, or there's about a 40% chance that exactly one of the couple's 5 children will have type O blood. Okay. So let's kind of continue with this scenario from the previous slide, but now we're looking to see what about if exactly 2 of the children would have type O blood. Okay, so because the method doesn't depend on the setting, we'll use S again as success and F again as failure. Okay, so to find the probability that specific 2 of the 5 tries, say, let's say that the first and the third, or the first 2 here are the successes. So we'll say success, success, and then the last 3 children don't have type O. So fail, fail, fail. Okay. So we know from the previous slide that we know now that the first 2 successes are going to be the 0.25 multiplied together, and then the last 3 are going to be the fails. So the fail is 1 minus the probability of success of the 0.75 times 3 times, okay? So the probability that the first 2 children would be type O blood and the last 3 not type O blood would be about 2.6%. Okay. However, there are several different arrangements in which 2 out of the 5 children could have type O blood, right? So we saw that in the last time, right? It may not be that the first 2 have type O and the last 3 don't, right? It could be that the first 2 do, the first one does, the second one doesn't, but the third one does, and the last 2 don't, right? And so on and so on. And there are 10 different ways to make this arrangement, okay? So, let me not jump to that yet, okay? So there are 10 different ways that you can show 2 successes and 3 fails, given these 5 children, okay? Those 10 arrangements, rather, are all here. Now, each one of these 10 arrangements have the same probability. We showed that in this last slide, right? There were these kind of 5 situations here where you can have 1 success and 4 fails, okay? But they all had the same probability. So all we did at the end was say 5 times one of these probabilities. Well, that's what's going on here, only we have now 10 situations because we're looking for 2 successes and 3 fails, okay? So the probability that 1 would be 0.02637. The probability of 10 would be 0.2637. So the probability that 2 children would have type O blood and 3 children would not would be about 26.4%. Okay? So note in the previous example, any one arrangement of 2 successes and 3 failures had the same probability. We saw that again in even the example before. This is true because no matter what arrangement, you'd be multiplying 0.25 twice and 0.75 3 times. So it doesn't change how you multiply. We can generalize this for any setting in which we are interested in k successes in n trials. So 2 successes in 5 trials, 2 type O bloods in 5 children. Okay. So the number of ways of arranging k successes among n observations is given by the binomial coefficient of n. Where are we here? Hang on. Of n over k here, okay, which can be found by n factorial over k factorial times n minus k factorial, okay. This goes back to the idea of combinations and probability, okay. We can take a look at it. The long ways we'll never do that. I will show you how, or I actually should say, I will remind you how to do that on a calculator in class, but it's very easy to do on a calculator. So this would be the idea that I would have 5 children over 2 successes. So into the calculator it would be like 5 choose 2. It would be the combination of 5, taking a combination of 2 given 5. Okay, so the binomial coefficient counts the number of different ways, it's the arrangements or combinations in which k successes can be arranged among n trials. The binomial probability is this count multiplied by the probability of any one specific arrangement, because we now realize that the probability of 1 is never going to change. It doesn't matter where the arrangement is, where the success is happening, or I should say where the success is may be happening. The probabilities are always the same. So multiplying that by how many times the successes can happen, or the arrangements of the successes, okay? So we get this formula here, where the number of arrangements would be that first part times the probability of success, so that was like that 0.25, times however many times, or to how many times that can occur, okay, times the probability of a fail. So that was the 0.75. That was going to occur to the n minus k times, which would again be in the last situation. So that was 2 successes. So 0.25 times the 2 success to the second, because we wanted 2 successes. Times 1 minus 0.25, so that was 0.75. That was the fails, not having type O blood, to the n minus k. So if I had 2 children that had type O blood, to the third power here, because I would have 3 fails. I would have 3 that do not have type O blood. Okay. So we'll just kind of run through the same situation. We'll up it to 3 children having type O blood, and this time we'll run through that formula, okay? So same scenario of those last 2 examples, okay? So now we're going to find the probability that exactly 3 of the children have type O blood. So we'll let x equal the number of children with type O blood. We know that x is a binomial distribution already. We have the number of trials fixed at 5 children, and the probability of each of those children having type O blood is the same, 0.25. So the probability that exactly 3 children will have type O blood would be found as the following. So I have 5. Okay, I have 5 children. I'm looking for 3 successes here, okay? that's going to have 10 arrangements again, okay? I want 3 successes. The probability of success is 0.25. If I have 3 successes, then I'm going to have 2 fails. The probability of a fail is going to be 1 minus the probability of success. So 1 minus the 0.25, which is 0.75, okay? This number I would have found using my calculator under my probability function on my calculator. Again, I will show you that in class. And here is the probability that exactly 3 children would have type O blood. So you're looking at about 8.8%. Should the parents be surprised if more than 3 of their children have type O blood? Okay, to answer this, we would have to find the probability that X now be more than 3. So the probability that they have more than 3 children with type O blood. Okay, in other words, it would be the probability that they will have 4 children with type O blood or all 5 children. So exactly 4 and exactly 5. So the probability, or exactly 5, I should say. So we're going to be adding together these 2 binomial probabilities. So we're going to now change our probabilities slightly, or finding them a little bit different, right? So now we'll have 5, sorry here, 5 children, but now we want 4 of them to be a success, meaning 4 of them will have type O blood. So success, probability of success times, we want 4 successes, probability of a fail, then we would only have 1 fail, plus the probability that exactly 5 will have type O blood. So 5, choosing 5. So all 5 having a success would mean that we'd have 0 failing. Okay, so the probability that exactly 4 would have would be a success would be 0.014, plus the probability that if all 5 would have type O blood, or all 5 would be a success, very, very small. So the probability that all 5 would be a success, or exactly 4 would be a success, would be 0.01563. In other words, since there's only 1.5% chance that more than 3 children would have type O blood, would tell you that the parents would be very surprised if more than 3 children would have type O blood. It's a very small probability that that's actually going to happen. And that's it for the beginning of the preview for Chapter 16.